This is coming to the end of our first week. We're going to try and knock off all the material on material properties today, which is the first week of the syllabus. And then next week we'll start being able to use some of those properties to talk about pressures in fluids, statics. So that's kind of our plan for today. So typically in a class I'll try and recap a little bit of what we talked about to try and put it in context very briefly. Of course you can go back to the YouTube notes as needed for that. But if you remember last time, we were talking about properties. Just we defined what a liquid and a gas was, all encompassed in fluids. I remember that in the figure I drew, I actually called what I meant to call a liquid a fluid in the little box. So you should remember that if you go back to your notes from the first time we met. I spelt dimensional wrong, I guess, but we talked about how apples have to be added to apples, and so we should be able to work with the typical critical components that we deal with, which are mass, length, and time, and also temperature. Actually, we didn't talk about temperature, but temperature in the book is used as theta. We talked about some fluid properties in terms of density, and the difference between mass, which is an invariant property, and weight, which depends on which planet you sit. We talked about equations of state in terms of the ideal gas law to be able to describe the behaviors of ideal gases, which conform to this law relating pressure and density. We talked about how it matters whether you compress them isentropically and insulated so you don't lose any of the entropy as you compress them. You keep the temperature that you gain in there. Or if you do them under isothermal conditions where you allow the heat to escape to the surroundings and to be no temperature change. And importantly, we use this to be able to say something about the compressibility of gases, which are related to the change in pressure that you apply and the volume change that results, or the change in pressure that you apply and the density change that results. So in one case, if the volume goes down and you have the same amount of mass in the system, you have to increase the density. And the reason for these negative and positive signs are just to be able to keep this coefficient as positive. And so that was where we left it last time. One of the reasons for talking about compressibility is because it figures into an important feature of solids and fluids, and that is related to wave speed. And so the things that we'll talk about today are wave speeds, viscosity of fluids, which we've talked a little bit about, vapor pressure and surface tension, and my guess is that's about as far as we'll get. And so that's the plan for today. And so you'll see the kind of style, I jump around a little bit between web-based movies and scribbling things down and using these notes ourselves. I do replenish the notes each time, so if I make any changes to this big packet of notes, this 50 megabyte packet of notes, I post the new ones on Angel. I just replace them. And so these will be there if you choose to use them. So you'll come to some equilibrium, I guess, in your note-taking as we go down the path. So we're talking about wave speeds. And we can think about wave speeds in different media. 3 years, I think, ago, it was the East Coast earthquake around this time of year. It was in August. And it turns out that you can get the compressional, there are a variety of different kinds of waves. We're using one form of wave speed here to communicate with me. The time it takes for my voice to get to your ears is governed by the acoustic velocity, the P wave velocity in air. And we can get that P wave velocity by this term here is what we've called bulk modulus. In air, the shear modulus, or in fluid, this shear modulus G is equal to 0. It's not 0 in rocks. It's roughly of the same order as K in rocks. And this is the density. So if you look at, you could do the calculation now for that matter, right? So you could calculate what the acoustic velocity in air would be, because we know that the modulus of air, or gas, nitrogen, which we're living in, a bit of oxygen as well, hopefully, is something of the order, we know this is equal to the fluid pressure, right? And we know that the fluid pressure is equal to 0.1 megapascals. meganewtons per meter squared. And so we know that. We know this is 1,000 kilograms. And so if you wanted to do that, we said that this is equal to 0 in air. And so the acoustic velocity in air should be something like, what's this? This is 10 to the 5 newtons per meter squared divided by 1,000 kilograms square root. So 1,000 kilograms is 10 to the 3. So it's 10 to the minus 3 times 10 to the 2. And so the 10 to the 10 to the 3 times 10 to the 2, sorry, 10 to the minus 3 times 10 to the 5 is 10 to the 2. And this should be in meters, Newton meters squared per kilogram. And if we take the square root of that, that should be 10 meters per second. Sounds very, very small. Sounds too small, in fact. Okay, in wave speeds, you guys should have corrected me, of course. What was wrong with this calculation for air? Well, for air, we tried to do this calculation with this equal to the modulus divided by the density square root. And what we did was we used the density for this, which is not of air, but of water. And so the result was a crazy value. So the density of air is of the order of 1 kilogram per meter cubed. We know that the modulus of air, relatively low pressures anyway, is about equal to the pressure of air. And we know at atmospheric pressure, the atmospheric pressure of air is 0.1 megapascal, 1 atmosphere, which is 1 atmosphere, which is also equal to 10 to the 5 newtons per meter squared. So if you use those values, get the speed of air, speed of sound is 10 to the 5 pascals, newtons per meter squared, divided by 1 kilogram per meter cubed. Square root of that is basically square root of 10 to the 5. And the square root of 10 to the 5 is the square root of 10 times the square root of 10 to the 4, right? So, which is about equal to 300 meters a second, which is exactly what the speed of sound in air should be. So, the previous calculation, you should have stopped me. It's not the density of water, it's the density of air that, of course, you have to use for this. So, I was confusing myself. Anyway, so if you look at the shear wave, because this is equal to 0 in a fluid, there is no shear wave in a fluid. But in a solid, this magnitude is roughly of the order of the modulus of the bulk modulus. And so in a solid, there is a shear wave. So that's when, in an earthquake, you feel the initial shock first, because it's traveling at the p wave velocity, this wave velocity here, which is the sum of these two, which has to be larger than just one of these. And then the destructive wave that comes later, roughly half as fast, is the one that does, if you take a skipping rope and you swing it along the ground, this is the one that gives the shear motion in the ground, which actually is the thing that shakes buildings to pieces and has most of the destructive force. So those relate to the velocities. That the P wave is my voice to you. Shear wave doesn't exist in fluids because the shear modulus is equal to 0. But the other wave that's of interest to us, which we've talked about, but we haven't derived the expression for, we talked about it last time in terms of when we just messed around with some dimensionless parameters. The celerity wave is the velocity of the wave when you have a free surface. So it's the wave in the ocean. So instead of being, certainly if I shouted here, if I was standing here and shouted, the wave for me would travel here to a receptor, to another person here, and the rate at which this would travel would be at this compressional wave in water, the acoustic wave in water, same as you get when you use sonar, for instance. But different from that is the celerity wave, which is the velocity of the surface wave, which if you had some kind of disturbance on here, you'd create a wave that would travel on the surface. And the velocity of this is proportional to the depth of the water multiplied by gravitational acceleration, all square rooted. And so you can work out what that would be. We're going to use an example for what happened roughly 2.25 years ago in Japan as an example. If you work, for instance, with the sea, which is, say, 1,000 meters deep, then the celerity wave is going to be gravitational acceleration, which is roughly 10 meters per second squared, multiplied by the depth, which is 1,000 meters. So the units of this are in meters squared per second squared, so square rooting that is meters per second. And so this is 10 to the 3, 10 to the 4, square root 10 to the 4 should be 10 to the 2, right? Equals 100 meters a second. And so surprisingly, it's very fast. That's the speed that a tsunami, for instance, goes across the ocean at, roughly the velocity of an aircraft, which is less than the speed of sound, which is why I can't quite reconcile that. Maybe you can tell me what's wrong with my calculation. And so these three different waves have some kind of impact on not necessarily our lives. I guess there was an earthquake here on the East Coast. I think the people on the West Coast were laughing at us about it. I know the people in my building, some of them ran out of the building when they felt it. That's what you're supposed not to do, because if the building's shaking and there's something on the roof that might fall off, then you get hit by it as you go out the door. But you can use the difference in these wave speeds to some benefit. And so many of you will know, certainly in your lifetime, right, 2.5 years ago, March 9th, 2011, there was a very large earthquake off the east coast of Japan, the Tohoku earthquake. The reason for the earthquake was that the trench here is the location where Japan on one side, Pacific plate on the other side dips underneath it. As the plate goes down relative to this plate, it drags, is subducting, it's being driven by the convection forces in the mantle, which is a fluid mechanics problem. But the plates are converging. The only way they can get past each other is for one to dive down next to each other. And in diving down, it pulls down this other plate, which is the plate which Japan sits on, where my watch is. And then all of a sudden, when this releases, then this pops up. When this pops up, all of a sudden, it displaces the fluid above it, which is exactly this. So this is the plate going down relative to Japan. It's done the other way. So this is Japan right here, and this is looking eastward. So this is the east, not the west. And when it releases, it physically pushes up this portion of the plate here, which then displaces the fluid above it. And that fluid being displaced above it allows a wave to move, a single wave, a soliton, if you like. And so if you look at these P-wave velocities, the P-wave velocity in the rock is something of the order of, say, 5,000 meters a second. If you use the correct modulus for rock. Modulus for rock is about 2 to 10, say 10 gigapascals. The S-wave velocity might be half of that, say 2,500 meters a second. And the velocity of the wave that's produced is something of the order of 100 meters a second. And so you can actually use this, and in Japan they do use it. So if you're sitting here on the trench, the depth of the water is about 1,000 meters, kilometer, which is the number we used. I think Tohoku is right here. The break on the fault was over 100 kilometers. The actual movement on the fault was something, the displacement from one side to the other was something like 100 meters. So what were 2 points that were next to each other were 100 meters apart a few seconds later. So it's a huge motion and a big displacement of water. And this distance here is something of the order of 100 kilometers. And so you can use these velocities to figure out, since you know that the velocity is equal to length times time. So if you want to calculate the time taken for it to arrive, you can do that just by rearranging that as length divided by the velocity. And you can use each of these velocities to calculate how long it takes to go, say, 100 kilometers, of the order of 100 kilometers. And if you do that calculation, you find out that it takes almost a minute for the P wave to come here, to come there, on coast. It takes almost twice as long for the destructive power to arrive, which is the shear wave, and it takes much longer for this to arrive. And so the innovation that you can do with this, I think it's sitting right here. So this is in one of the buildings in Sendai, which is the city that we showed that was closest to the onshore part of that, very close to Fukushima. It's just a radio transmitter, which you put geophones on the fault, right at the fault. So when it breaks, you know it's broken right there because the wave arrives straight away because it's so close. You send that signal electronic by wireless, which is traveling at the speed of light, so it arrives almost instantly at the receptor. The receptor here happens to be 100 kilometers away. And so an alarm goes off, and hopefully it gives you 50 seconds or a minute to quietly evacuate the building, get outside where you might be safe, and actually gives you almost 2 minutes, right, before the really destructive part arrives. And of course, the interesting thing about the Tohoku earthquake was that it was a huge earthquake, magnitude 9. There's maybe one of those every decade. The previous one was about 10 years ago. The Indonesian earthquake was close to magnitude 9. So they're very big events, but almost none of the loss of life occurred because of the shaking or damage to buildings itself, but almost all the loss of life occurred due to the resulting tsunami that occurred. See if this is going to work. And so we showed the Poseidon adventure last time. Is this running? It's thinking about running? Yeah. Don't know why it's not running. That's doing something. Let me refresh it. You can probably tell what it's about from the title on it. Yeah, it's running now. So what happens is one part of the seabed goes down, the other part goes up. Basically you have a wall of water which can't stand as a wall of water, so it dissipates as a wave. And so this happens to be the Coast Guard that were floating around out there. We looked at the Poseidon adventure, we had this crashing wave coming over a liner, but out to sea is actually, it's bigger than a few centimeters, but this is climbing the actual wave. With a bit of excitement. Of course, they could tell, I'm sure they wired it to the shore to say what was coming. I mean, people expected it, people are ready for that. Certainly if you walk around on the west coast of the US, you see tsunami warning signs, which means if there's an earthquake, just go to high ground. That's really all it is. But out to sea, of course, there's no single crashing wave. And so the difference in the timing of these events means that they occur because of different physical circumstances. The solid wave through the rock is fastest. Of course, the speed of light through air is the fastest of all of them. It's basically instantaneous. And I think this is probably over now, so we'll stop that. Doesn't really like to stop for some reason. We don't want to watch any of the other things. Come on. My computer's spending too much time thinking. It won't give me the screen back. So I hit escape, it doesn't make it smaller. Okay, perhaps I'd have to do this. Has it locked on me? Well, it hasn't locked on the other things yet. Anyway, so it doesn't want to go back. Am I going to have to close those? Corn, well, we don't really want that. Corn. I know enough to know what corn is. I won't subject you to that. I might have to turn it off, right? I'm going to kill that one. That's what I'm going to do. Yeah. Bye-bye. Bye, Felix. So let's do this one as well. So this is interesting. So let's wander through. So this is Kamaishi. Used to be the Pittsburgh of Japan. It used to be the steel town that when, in the post-war years, when steel had been made in the Second World War in Pittsburgh, the Japanese, in the post-war years, put Pittsburgh out of business. I think then the Koreans put Japan out of business in steelwork. And then the Chinese put Korea out of business. I think that was kind of the natural ascendancy. But Kamaishi was a steel town. It has an iron ore mine close by. It was a site for an experimental project in radioactive waste disposal. So I visited there one time. It's on the east coast of Japan, very close. It's to where we looked at where that radio receiver was. And this is a film that was begun at the time of the earthquake. The reason they started filming it, because now the shaking has occurred and may be finished. Otherwise they wouldn't be recording this. This is some people up at high ground just hanging around. So I will ask either one of you or me to set your timer for 5 minutes, and we'll disappear from this and we'll come back. This is a very interactive class today, isn't it? If I can't get my timer going, I can get it going for 5 minutes. Alright, so I'll put the sound off and we'll come back to this in 5 minutes if we can. Okay? And I guess while we're... And so, of course, you all know about the Tohoku, the Japan earthquake. So this is a building at the university at Sendai, which is the town closest to the earthquake. And you see, in a very orderly way, the Japanese have, a year after the event, almost on the anniversary, have isolated all the cracks in the buildings, and the different colors mean that the sequence in which these cracks will be repaired, the most urgent ones first. I'm not sure what the color code is. And so very orderly. And of course, this is what the coast looked like, what would have been a village beforehand. This is in March, I think March the 10th to 2012. And you can see that there's some structures left, but where everything would have existed before, there's just absolutely nothing. A Shinto temple, but everything else has just been pushed off its foundations. It's all the silt has been washed up by the motion of the water over the top of it. Wells, former burial ground, and all the rice paddies, which would be on the coast, which would be full of fresh water to make rice, of course, are inundated and are useless until they can regenerate themselves by flushing out the salt that's present in those places. Buildings that survive, this is a 1, 2, 3, 4-story school. The 4th story looked like it survived, but everything else, I mean, just an amazing height of these things. Not sure what else we've got. Some of the very sturdy buildings survived. Everything, these would have been quite well built up areas. That's just snow. Railway lines. Some of the deaths were, of course, trains that got swept off railway lines which travel up the coast. And this is the one I'll leave you with, which is, you know, obviously that's not the third. It's not a roof parking lot on this. It's a car that ended up there by being pushed there by water. Anyway, so amazing event. So I think 18,000 people died. Almost none died in the actual shaking due to any buildings collapsing, but all died because they just didn't get out of the way of the tsunami in time. Tragic event. So let's come back to that. So wave speeds have something of interest for us. So, okay, enough for wave speeds. So what else are we going to talk about? So I guess we'll come back to that in a few minutes. What am I looking for? I'm not trying to make you sick by rolling through this. So we talked a little bit about wave speeds and how they are controlled as celerity waves on the surface and as body waves in the material, and their different velocities. The other property that we might spend some time talking about is viscosity. And viscosity is something that's important to us because if you're petroleum engineers and you want to suck fluid out of the ground, the resistance to sucking it out of the ground is controlled by the viscosity of the fluid. It defines the amount of energy you have to do to be able to pull it through the pore space in the matrix of the reservoir rocks. And the basic expression that describes viscosity is Newton's law of viscosity. It's one of our favorite guys in this class is Isaac Newton. And it just says that the shear stress that you have to apply to a fluid to get it moving is proportional to a constant, which is called the viscosity. It has units of stress times seconds, stress times time. Typically they're Pascal seconds. in SI. So the shear stress that you have to apply to move a fluid is equal to a constant called the viscosity, or a material constant, and the shearing rate in space. So dV is the change in velocity, and dy is with location. And so it's perhaps most easily shown with this diagram here, is that the idea is you take a fluid and you float a plate on it. Then you start pulling that plate with some force. The shear stress that's applied on that plate will be equal to the force that you apply in the horizontal direction divided by the area of this plate, right? This red area here, this plate here. All right, a brief reprieve. 6 minutes and 31 seconds. What's happened? Nothing yet. Okay? Very brief reprieve. So shear stress we have, right, which is what we need. The shearing rate is the velocity of this plate and the appropriate boundary conditions. So the idea is that a molecule of fluid which is sitting next to the plate is physically attached to the plate. So when you drive the plate at some velocity, that molecule of fluid travels with it and drags all of its friends along with it. But the fluids next to it, it drags only a little bit as fast, because the other boundary condition is that this static bottom here isn't moving. So you have two boundary conditions. The bottom doesn't move, so there's zero velocity here. The top moves, and so there's a velocity v. And so if you look at the profile of velocity relative to, in this case, y, then it looks like this. Right? And of course you know that if we try and draw this as a little differential, this is dy, and this length here is dv. You could take it as the total amounts of these as well. You could look at this as being v, and you can look at this as being, say, y depth. And so in this particular case, the change in velocity with depth, dv dy, is just equal to the velocity of the plate, let's call it vp, divided by the depth of the fluid, which in this case is y. Well, partial derivative means it can vary as a function of other components, and this means it can only vary as a function of one component. I wouldn't get hung up on it. It is a partial derivative, dv dy. This is wrong in this particular case. It's usually dealt with as this. So that might not be a very satisfying answer, but take it for now. So in other words, we assume that this is constant in this particular case. And so if you're dragging this across with some force, you can measure the force. If you measure the force, you can calculate the stress. If you calculate the stress and you know the velocity, you have everything here to be able to calculate what this one component is. And so if you want to measure the viscosity of something, typically you do that. You take a sandwich of it, you put a plate on the top, you move the plate, you measure the force you have to apply to the plate to move it at some velocity, and the only thing that you don't know is the viscosity. And so now if you know the viscosity of a fluid, you can apply that. It's not a meaningless exercise. You can apply that to different geometries, say where you push a fluid through a tube, which might represent a pipeline, or it might represent the pore of a porous medium, and you can calculate what the drag force you have to is applied, and therefore the force, the fluid pressure that you have to apply to push the fluid through there. And so you can do that. We'll deal in this class only with Newtonian fluids. And so Newtonian fluids are ones where this value is a constant and doesn't change with the rate at which you shear it. So this would mean that you're not shearing it at all. This would mean you're shearing it quickly. And this would mean if you're not shearing at all, then you'd expect that you don't apply any force. You don't have to apply any force to it to not move it. If you apply a force to it which is larger, then you'll move it at some velocity. If you double that force, then you'll double the velocity that it'll be pulled at. So a linear fluid, a Newtonian fluid, is one where if you double the stress that you apply, you double the velocity at which you shear it. Just a linear system. Not all fluids are like that. Some actually have an initial threshold stress that you have to overcome to move it, sometimes called plastic fluids or Bingham fluids or thixotropic fluids. They mean that initially it's kind of like a solid, and so typical fluids that are like that are actually drilling muds, for instance. Drilling muds are just a suspension of clay particles, sometimes with denser materials like ground up barite to give it some extra density so you can balance the fluid pressures at depth relative to the weight of mud in the column so your well doesn't blow out. But typically drilling muds, if you don't agitate them, they become solids. Once you start agitating them, then they become fluids. So they start off, if they're no shearing rate, they actually have some strength. If you agitate them, then again they have some kind of viscosity change with the shearing rate, but they'll behave then as fluids. So the only ones that we'll deal about in this class are actually Newtonian fluids, linear fluids. And so relatively straightforward, a law that we'll use all the time. And actually I think a law that's applied in one of your homework examples. I just caught someone, oh yeah. We'll come back to the homework example. What's happening? So the earthquakes happen, 12 minutes going, boats going out to sea. What's everyone talking about? Nothing yet. Okay? Okay. 12 minutes in. Okay. So one of your homework examples, for instance, I think, deals with a piston being pushed through a larger annulus. And so you could imagine that if this piston, is going through at some velocity, and it's relative to this static annulus, and this is a fluid in here, then you could imagine that the appropriate geometry would be that the fluid at this point is going with zero velocity, the fluid at this point is going with some velocity v, and so this profile of velocity would just be this. So this would be dv, bless you, dr in this particular case. And so you can also write this as being equal to viscosity times the change in velocity with radius. So the other thing to recognize is that it's the velocity in this direction, but it's relative to the distance in this direction, right? So it's not the change in velocity along the length at which it's flowing, it's the change in velocity perpendicular to that direction. And so here, if you know the velocity of this thing, then that's just going to be equal to the viscosity times whatever the velocity of that tube is divided by whatever the distance is, delta r. I think that's one of your questions anyway. And so if you want to know that, you know what these geometry components are. Perhaps you know what this is, and maybe you have to calculate the force that's applied to do that. And of course the force that's applied to do that is just going to be the shear stress which is applied on this boundary multiplied by the area of the boundary. So it'll be the circumference multiplied by the length, I think. So I think that's one of your questions. So that serves a purpose of at least being able to talk about that. So viscosity is an important parameter in what we'll deal with because it, for instance, conditions how quickly you can get fluids out of the subsurface or into the subsurface if you're trying to drive them that way. Very simple relationship. Okay? We're going quite quickly through this. We're going too quickly? I don't hear any comments. So. All right. Yeah. Sorry.
We take the radius as the difference of radius of inner piston and the outer.
You would take one of the radii and you'd be equally correct in using either of them. I mean, the idea is that they're probably very close to each other. So I would take the inner radius and use that. You just need the area of the plug that you're pulling, right? It's an approximation. Yeah, it's an approximation. Other questions? Was there another question?
Go back to that equation.
We can. Oh, just to write it down? Okay, fine. All right, next topic. Vapor pressure. And so vapor pressure, of course, relates to when we boil things. Sorry, didn't. Yeah, it'll be on YouTube, so you'll see it. We won't talk about wave power. We'll talk about which did I want? Pressure temperature diagram. Yeah, that's what I wanted. Okay. See if this works. We're doing this in real time. Isn't it amazing? See if I can find that on my desktop now. Okay. All right. So, vapor pressure. So vapor pressure, of course, is the idea that you can boil something by changing either the temperature or the ambient pressure at which it lives. Fluids with a free surface always have an exchange of molecules across it. If you net lose the liquid to the air, then you're evaporating. If you net lose the gas to the liquid, then you're condensing, just by definition. And where we sit at current pressure and temperature conditions is shown in this diagram. This is a pressure temperature diagram for water, the most common subject on the planet. And so we sit at 1 atmosphere. So I think where we sit right now is here. And we sit at room temperature for us is something of the order of 20 degrees centigrade. Absolute 0 is 0. Freezing point is what? 273 Kelvin. So 293 Kelvin is where we sit. So this is somewhere here. Let me try and draw a figure. Is that about right? Yeah. So this is where we are right now in this room. We sit at 1 atmosphere. 1 atmosphere is 0.1 megapascals, 100 kPa, 14.7 pounds per square inch, whatever you want to choose. Those are two different. And so if we had water in here, as you do in some of your flasks, it would be liquid. If we increase the temperature by about 100 degrees to would be 373 Kelvin, which would be this point here, it would boil, it would vaporize. That's one way that we can actually make it into a vapor. This comes from Canada, I think, right? Hence the spelling. I think it was, right? What's the site? Yeah, UWO is University of Western Ontario. In London, Ontario. But the other way you could boil it, of course, is to drop the pressure. And so if you could suck the air out of this room, or take it up in an airplane, then you'd actually find that you'd actually intersect this curve, which is the boundary between liquid water and steam, at the same temperature as we're living at now, but at a lower pressure. And you could calculate essentially what that would be, and it would be something like dropping it by 2 orders of magnitude. So dropping it almost to 0, essentially putting a vacuum on it. So you'd also almost have to put a vacuum on it. And so the other consequence of that is if you take a stove up to the top of Mount Everest, which is about 30,000 feet above sea level, and 30,000 feet is about 1,000 meters, then you could calculate from what we'll do on... Did I start again? I don't think I did. Well, we may be too late. You could calculate, for instance, what the boiling point would be of water at that elevation. And you know simply from looking at this that as you go up, the reason that we sit under 14.7 psi pressure here is that we have a whole column of air sitting on top of us. If you go partly up in that column, then you have less of that column impinging on you. And so you'd expect that the force that you have to apply against that is less. And so you know that the pressure goes down as you go up. That's why they pressurize airplanes, so you can actually breathe. You get enough oxygen into your lungs. So you'd know that as you increase in elevation, the pressure would change, and therefore the temperature that you'd have to apply to boil water, say if you were at this temperature, so if you were at only 0.1 of an atmosphere, 0.01 megapascals, then it would only have to get up to something like 320 Kelvin, which is probably about 50 degrees centigrade, right? 270 is freezing point, 0 centigrade. So 320, did I do that? Yeah, so this would be the magnitude here, right? So this magnitude here would be, is something like 320. So the difference between the room temperature, and so this is 290, so this is about 30 degrees. So you'd have to increase the temperature above room temperature by 30 degrees, which would be 50 degrees centigrade to get it to boil. And so that, I think in the notes it's wrote, so why would that be important if you're trying to cook? Well, if you're trying to cook, then you only get something to 50 degrees, and so you can't actually heat it up the same way that you'd want to be able to cook it. So cooking always relies on the fact that you bring something to a boil and keep it that temperature for a certain amount of time to change it chemically in some way. And so the time for you to be able to cook something would actually increase because you wouldn't be able to raise the temperature so high if you're boiling it in water. And so vapor pressure is merely the equation of this line. The equation of this line is given in tables, and we don't really need to look at them here, but the basic idea is that in going from a liquid to a vapor, you cross this boundary, and usually you can also go the other way, of course. If you reduce the temperature enough in a fluid, you make it solid. So in this case, this would be making ice, just by freezing it at 0 degrees centigrade. Boiling it at 100 degrees centigrade. If you do it at a different elevation, then you'd still likely freeze it at the same temperature. You know, this doesn't change. This is basically a vertical line here. But now the temperature which you start to net evaporate it, boil it in other words, is actually much reduced. And I don't know if I have that somewhere. I mean, sometimes I didn't run through this before to see exactly what it was. It should be condensation on the wing of a plane. Yeah, you can see it. So sometimes you see this. If you take off in some of these very jets with relatively powerful airfoils, typically above the engine, you'll see this streak of white vapor. And so what that is, you know that on the top of, you can see this coming over right here. Someone's taken, this is the engine, and this is coming over the cowling in the top. I think, did I see it here? Yeah, you see some of the idea here. As you go across the top of an airfoil, the area on the top is at a lower pressure. And so at that lower pressure, what happens is that you are doing what? If you increase the pressure, you compress the gas. If you decrease the pressure, you expand it. So you know that when you compress a bicycle pump, it gets hot because you're compressing it. The opposite happens if you expand it, is it becomes cooler. So as it expands, it chills. When it chills, it actually condenses the vapor that's in there out of the system. So that's occurring as a function. The pressure change is driving a temperature change, and that temperature change is allowing the vapor to be condensed in that particular case. So all right. So where are we with this? So we talked about this diagram. Okay. So there's some notes in your notes on that. I won't go through them. It talks about what happens, and there's also an example for viscosity. I'll let you go through that yourself. There's some notes on vapor pressure. It basically says exactly what I've said. I mean, I think there's some important applications of vapor pressures. It used to be that water running down dams, when it runs down a spillway, because it increases in velocity as it goes downhill, if it increases velocity too much, then it will actually go into, it'll be such low pressure that it will cavitate. It'll go into tension. It will fail in tension. And as it cavitates, it will actually rip pieces of concrete off that and destroy it. So the Tarbela Dam in Pakistan was the first one where that was observed. And of course, if you look at modern-day nuclear submarines versus, say, World War II submarines, the propellers on the backs of those things are very different. On World War II submarines, they're tiny little propellers. They spin very quickly, and they make lots of bubbles because the fluid passes very quickly over the top of them, and it cavitates. It fails in tension, and it makes little bubbles that burst, and you can hear those bubbles. And so if you want to run deep and silently, then you don't want that to happen. So what you have is much larger blades, almost like the propeller of a plane, which move much more slowly, and as a result, they don't have any of these cavitation effects attached to them. So, again, I won't show that here, but that's the reason for that. So, okay, let's stop. So we missed 20 minutes. Let's go back to... And we won't get through the last part here. So we've kind of jumped around, so you haven't seen, but all the foreground, we saw some boats going out to coast. You see some boats in the distance. You see something coming in distantly. We do have enough time to watch it. I'm going to bring it forward a little bit. Tsunami, of course, as you know, I'm sure, is a Japanese word. Anyone know what it means? Harbor, I think the literal translation is harbor wave. We refer to it as tidal waves. I think tidal wave is quite an apt description, right? Because it's not really a crashing wave that comes in, as you'll see. It certainly has a crest to it. But what's happening also in the foreground is that just the sea level rise is rising with time. You see from the timing, I presume that this was begun. There's no reason to take this movie, of course, right? Before you know there's an earthquake. So you do it at the P wave arrival when you get up onto the building. This doesn't like me very much. It's not moving. Wow. Put your timer on for 2 minutes. Maybe I need a more powerful computer. It doesn't seem to like anything I tell it to do. Okay. Yeah, let me go back. Yeah. So, don't have very good. Okay. Yeah, let's watch this. So it really is a kind of gradual elevation of the water level. You see this stuff out on the fringe in the harbor moving in. It gets damped out, I think, as it moves into the harbor, so it doesn't become a crashing wave per se. But it's certainly raised up over a quay, right? This crane, of course, was sitting on a quay before. This is the wave broiling on the horizon line. And as I think they scoot round to look at the right, to their right. Come on, come on, come on. Yeah, we could go back. Okay, moving portals. So now this is the seawall, which were built to heights to be able to guard against the expected heights of these tsunami. But now all it is this kind of relentless increase in elevation in the sea level with time that slowly, ultimately overtops the defenses, which are a seawall that rings this particular city's coast, which is a fishing village as well as being a steel town. And then ultimately, as this goes on, as we come to the last 3 minutes of our time together, as you'll see on the top of the screen. Oh no, don't pack up yet. I skipped. And so all of a sudden it goes over the top, and it's just this relentless elevation change that keeps on rising and rising and rising and rising, ultimately go down because it's a wave. It just has a very long wavelength and therefore has a very long period as well, and an amazingly destructive event. And so the conventional wisdom, of course, for safety from these things anywhere on the coast is typically if you live in flat-lying areas. I remember after this I was in LA, driving around in LA, And you couldn't help but notice as you drive around in parts of LA, it is flat as a pancake as you go towards the coast. And so in places like Huntington Beach, where there are really no tall buildings, it's all single-family dwellings that are one story, there's no refuge. But the conventional wisdom is that the refuges from these are to build tall buildings on the coast. They're sturdy enough they don't get washed over, but you just elevate yourself by running up into them, and you start taking movies like these guys did here in this particular case. The final topic to deal with is of surface tension. And so surface tension relates to the adhesion on a solid surface. There can also be interfacial tension between two fluids. Of course, in this case, if there's air above a surface, free surface, and liquid and water in this case below it, then you have two fluids and there's an interface clearly between them. But when we talk about surface tension, we're talking about the adhesion that occurs between a liquid typically onto a solid. And so this is the classic example of a capillary tube, a thin, small diameter tube that's pushed into a fluid. And if the fluid is attracted to it, it adheres to it, hydrophilic, it loves the glass that's here, then the fluid will tend to rise. And it will rise because of the adhesion force which is applied at the corner, which will give some tension to this. And so one way to analyze this is to be able to understand the magnitude of the effect and define the magnitude of the interfacial tension that allows this to happen. And so in basically characterizing this, the features of it are that if it is hydrophilic, then the rise in the tube will be above the datum. This is the datum of the water that's pushed into, and the portions of this curvature will be above this line here. And if the fluid happens to be hydrophobic, it's not hydrophobic, but solid phobic, it doesn't like it tries not to maximize its contact with the solid that's it's around, then the angle that it makes in this case is will be in the opposite direction. The force will be down, and as a result it will depress the column of fluid below the ambient level. And also you notice that this coupling between the tube and the fluid on the outside is also in the opposite sense. And this is important in lots of instances, particularly in places where this diameter is relatively small, because when this diameter is large, as we'll see, this effect is very, very small. And it comes to bear, for instance, in cases of porous reservoirs, where you can think of one of these tubes as the pore space, the pore throat between a couple of grains. And if the adhesion forces are large, if, for instance, you have a liquid in there with a gas, then sometimes you can't physically push this liquid through the pore space. So it has important ramifications in the wetting of reservoirs. So this would be called wetting fluid, because the angle that this makes with the vertical direction in this particular case is less than 90 degrees. This would be a non-wetting fluid because the angle it makes is actually greater than 90 degrees, which 90 degrees of course would be here. And so what we can do is we can analyze this to be able to say exactly what the height of the rise would be. And if you wanted to, you'd be able to measure or define the interfacial tension of the fluid from this, this geometry that you measure. And the key observation is, as we'll find out later, is that if you look at moving in a fluid from one location all the way to another, and you could make that journey through the fluid alone, then on any horizontal plane, the fluid pressures within that fluid have to be the same at each elevation. And so the fluid pressure here, which has to be only atmospheric, because that's what it sees, has to be exactly the same as atmospheric at this point here. So that physically means that you could physically cut off this tube at this point here and lift this whole column of fluid upwards and do basically a force balance on that. So that's the standard analysis that's applied to this. So that's the idea here. So you can cut this tube off at this particular location. You can remove the fluid from below, and around some average height of this thing, you can basically look at a single tube a fluid, where the force balance that you want to do is a resolved force acting upwards, which I think is T, and a resolved force due to the weight acting downwards, which is going to be equivalent to the volume of that cylinder multiplied through by the unit weight. Of course, the unit weight is equal to product of density and gravity, so this includes the planet we're on, for instance. And so we can evaluate what each of these components are. The shear force acting upwards is going to be given by the interfacial tension, which is the magnitude of this incremental stress that's applied around this periphery, multiplied by its circumference, and multiplied by an angle that represents the component of this which acts in the vertical direction. So typically if there's a contact angle like this, theta in this particular case, the magnitude of this will be T, which will be the interfacial tension times the circumference in this direction. But to be able to get the resolved component, which is in the vertical direction, then we need to multiply by, in this particular case, cosine theta to get that. So the circumference is going to be 2 pi r. And if you look at those components together, whoops, you'll see exactly that's the case here. So 2 pi r is the circumference that we have. Sigma is the interfacial tension, which is a property of the fluid and solid. And cosine theta is the interface angle that it makes. And you can equate that with this weight of the system, which is going to be equal to the volume of the column, right? Pi r squared is the area, and it's of height h, and the unit weight of this as well. And if you rearrange that, you can define the behavior in terms of this expression. The height rise is going to be proportional to the interfacial tension. The higher the tension, the higher this rise will be, and inversely proportional to the unit weight of the fluid. So more dense fluid, it has the same force pulling it up, but it's denser, so you can't pull it up such a high column. And also inversely proportional to the radius. You reduce the radius, and you proportionately increase the height rise in the column. So those are all intuitive behaviors that we look at. So that's one thing to be able to calculate the height rise in a tube, and it has, as I say, ramifications for flow in porous media where you want to displace oil by a different fluid, say water. They don't mix, they're immiscible with each other, and therefore you get surface tension occurring at the interface between those two fluids. They happen in that case to be two liquids, but the same principles apply. So another slightly different application for that, two different, well actually this one, do this one first, is the Phenom Eter. It's kind of an interesting idea. Let's see if we can increase the height. Well, actually, you see a bunch of these things. So this is, looks like this guy's sticking up his nose, right, in this particular case, but he's not, obviously. And so what you see here is this implement, and the basic idea is really quite straightforward. It's a small capillary tube that has a hole in it all the way through, has some gradations in it, and has a little cup at the top. You put your wine, as is suggested by the Phenom Eter in here. You purse your lips over the top and push the wine so it actually goes down this tube and drips out the bottom, and then you set it. And then you turn it upside down. And you turn it upside down, and then you read the gradation of where exactly the level will be in this vertical tube, and you can do the balance there to be able to figure out exactly what the magnitude of the alcohol content of this would be. Because of course the alcohol, so the rise in this tube is going to be a function of two things, as we saw in this previous equation, right? It's actually not a very different equation that we'd have to use in this particular case, right? So you have a height of the column, which is what you're measuring. You know hopefully the diameter or the radius of this, and so you can use this particular equation to be able to define this behavior. So the material properties, so this is what you can measure. We'd assume probably, well, you don't have to assume this because you can calibrate it with real samples of wine of which you know the alcohol content. But typically we assume that this cosine theta is equal to 1. In other words, it's the angle is equal to 0. And if that's the case, then this height rise is a function of the interfacial tension and the unit weight of the fluid. And so both of those might change as a function of the fluid you have. You could imagine, for instance, that the interfacial tension might be a function of the percentage of water and the percentage of alcohol that's in it, because they have different physical properties. These are miscible with each other. Obviously, in wine and beer, water and alcohol are mixed. And also you can imagine that gravity and the density of the fluid, density particularly, not gravity obviously, would also be functions of this as well. And so if that is the case, then you could use the measurement of this height of the column to be able to rationalize exactly what the alcohol content would be. And that's exactly what is done in this particular case. So that's kind of a nice, interesting example. The other interesting example or observation, I think, is this. And this is it's a video, I think. You can hear it right now. It's in a place called Jinan in China, about an hour's flight out of Beijing to the southwest. And it's a spring in limestone in this town. And what's floating on the water there, you can hear the background squeals of kids, is a coin, an aluminum Chinese coin. And you see that it's just floating. It's made of metal, but it's still floating. And so you can apply the same kind of analysis to be able to analyze that behavior as well. And so, whoops, I didn't want to do that. Okay. So if we do that, you'd go through the same kind of analysis, you could imagine. If you wanted to do the calc, I'm looking for a piece of paper to be able to do it on. I'm going to do it on right here. And so how would you analyze that particular case, right? You have a free surface, you have a coin sitting on top of it, would be one way to do it. I suppose you could also do it as a coin which was sitting just below the surface with this force coming up. Let's not do this one because we have to take into account buoyant weight of the coin in that particular case. So let's assume that the geometry is this, and you have a force that's applied up due to this. You have a weight that's applied due to the weight of the coin, and again you can just do, actually it's exactly the same mass balance that we did before, right? Because now, although it's not the fluid anymore that's being lifted up, it's actually the weight of this particular coin, which isn't fluid but it's metal. And it has some height attached to that, has some radius attached to that, and you can do the same balance. So that the upward force is going to be equal to what? It's going to be the interfacial tension, and it's going to be the circumference, which is 2 pi r. The vertical force is going to be equal to the density of the metal, gravity, and its volume, which is going to be equal to, the volume is going to be equal to the height multiplied by pi r squared. And these two, just by resolving vertically, are going to have to be equal and opposite to each other, so that they're equal to each other. And so you can merely equate these, and if you do that, what can we get rid of? We can get rid of the pi's in both cases. We can get rid of one of the r's in both cases. What do we want to determine? Well, I guess the question is, what's the metal? And I suppose what we might want to figure out is what's the density. So if you rearrange them in terms of density, we get the fact that density is equal to, taking this one, interfacial tension times 2, and if we divide through by gravity, height, and r, gravity, height, and radius, then we can use that to be able to figure out exactly what these components are. So the interfacial tension is given by, for water, is equal to 0.08 newtons per meter. It's per length around this, so it's this force is acting up here, and it's this is applied just on this contour, if you like. Actually, it's on the bottom contour of this. It's multiplied by 2, and gravity is roughly 10 meters per second squared. Height, don't know what the height is. It's of the order of a millimeter, I would think. You know, typical thickness of a coin is something of that order. So it's 10 to the minus 3 meters. And the radius, well, there was no scale in there, but it's about an inch in diameter. So an inch is 2.5 centimeters. So it's of the order, the radius is of the order of 1 centimeter, which is 10 to the minus 2 meters. And so if you look at those together, 10 times 10 to the minus 3 is 10 to the minus 2. So this is 10 to the minus 4 in the denominator. So that's a multiplier of, so this is equal to 0.08 times 2 times 10 to the 4. It should be in kilograms per meters cubed. You can check the units. And so this is 0.16 times 10 to the 4, same units, kilograms per meters cubed. Or if you put it into more usual terms, it's something, it's 1,600 kilograms per cubic meter. So we know that water is 1,000, so it's a metal that's denser than water, which, yeah, we think that all metals are probably that case. The actual density of aluminum or aluminium, depending on how you want to pronounce it, is something of the order of about 2,700. So we haven't guessed some of our units quite correctly, probably, but it gives you some order of magnitude guidance. And of course, we've made things a bit simple, but that wouldn't be the reason here. But it gives you some order of magnitude estimate of what the density of this might be. Perhaps we've used the wrong thickness, perhaps we've used something else, but just it's in at least a factor of 2 off isn't so bad. So that's another way that we could use our newfound knowledge to be able to kind of analyze these interesting physical systems. Okay, that's it. We've covered pretty much all the material I wanted to cover today. Just to go back to what we've talked about. We've completed the last 4 of our material properties that we wanted to cover. And those were that we looked at wave speeds. We saw how they vary in body waves and celerity waves, and how they impact, things like earthquakes and tsunamis are governed by these behaviors. Viscosity is a property of fluids which says that the shear force that you apply, or shear stress that you apply, is proportional to the shearing rate in space. Vapor pressures, and applied it to an airfoil. And finally, we've talked about surface tension and applied it not only to a venometer, but also to floating a coin, unusually on water. So that's kind of where we are now. So next time, what we have a chance to do is we have to use some of these properties. And the properties we'll use are typically density and gravity, as defined in specific weight. And use that to be able to, for instance, calculate how fluid pressures change as a point as you go up or down in the fluid, and also as those fluids are accelerated. So that's our next task, is physically to be able to use some of these relationships to be able to make some engineering calculations of use to us. Okay, thank you very much.